for the next talk, we are going to hear from Brian Dandurand, who is a postdoctoral researcher at Argonne National Laboratory. Before Argonne, he was a postdoctoral researcher at RMIT in Melbourne, Australia, and also got his PhD from Clemson University in the mathematical sciences. He has expertise in nonlinear optimization, stochastics, mixed integer programming, and multi-objective optimization. And here is his talk.
Welcome. Thank you for watching this presentation. I'm Brian Dandurand.
The volume is again pretty low.
Michel Schanen. I'll talk about our contribution for this conference. We are funded under a Department of Energy grant and also LDRD grant. We addressed a problem of a security constrained optimal power flow. They're like optimal power flow problems that need to be robust against any k number of contingencies. Such a problem, the number of contingencies grows combinatorially and choose k. So typically, such a problem is addressed with a subset of the possible contingencies, especially the most severe ones, which we identify through solving a bi-level maximum optimization problem. We have an upper level attacker problem subject to a budget that anticipates an optimal defender response from the lower level. And these types of problems are, as you see, well studied. So this is the upper level attacker problem. The budget is capital K. We focus on lines and transformers as by the Greek letter xi, which is either attacked or is not, either 0 or 1. This is a quick layout of the defender subproblem. So P bar, Q bar, these are target power flows that meet the power balance for each node. They need to match what the power flow law dictates when the line or transformer is on. Otherwise, the targets need to be 0 when the line is off. And if that's not realized, we have an optimal value that's positive, which means that the defender was not able to avoid load shedding or excessive power generation. Typical approach, reformulate the lower level, say Lagrangian duality, to get a single level problem. In applying the Lagrangian duality to the original lower level AC problem, we get an implicit relaxation. In fact, it's equivalent to as if we had applied the Lagrangian duality to the an SDP relaxed version of the AC lower level problem. That's true under constraint qualification. What we're solving, even with SDP, is a relaxation of the original bi-level problem. And there's a hierarchy to relaxations. And then there are other relaxations like the quadratic constraint, which in theory neither dominate nor is dominated by the SDP relaxation. A related work addresses the single level reformulation using the SOC, the second order cone relaxation of the defender level problem. And this single level reformulation is a mixed integer SOC, which can be solved by off-the-shelf solvers. We consider a tighter relaxation of the lower level problems, such as SDP, and we consider that with the understanding that there are trade-offs. SOC problems are easier to compute, SDP are more difficult, but they provide more accurate assessment of the contingency. These are just some examples from another related paper that under second review, where we see that the SOC model often evaluates the contingency as 0, whereas when using tighter relaxations of the lower level problem, we get non-zero. So these contingencies are substantial. When we only see that trend increase as the budget increases. With that in mind, in applying SDP relaxation, we have the state of art being interior point solvers. But they don't scale well with the size of the SDP matrices. Although to some degree, this setback is addressed through chordal decomposition, which we also use. We would like to improve this tractability of solving SDPs. We looked into using new developments with GPU architecture, but they cannot handle the linear algebra required with the interior point method. And also warm starting is an issue with our bigger picture purpose in branch and bound. Thus, we consider alternatives to interior point with first order methods, and so these approaches in power flow have also been studied. We apply an approach that's most closely related to the projected proximal bundle method. This uses some ideas from bundle method, but it also resembles ADMM functionally. The cutting planes provide robustness with respect to initial choice of penalty parameter and faster convergence. Put another way, we don't relax as many constraints in the Lagrangian reformulation. No, we don't relax as many constraints in applying the splitting proximal approach. So we have a reduced dual space, but more expensive subproblem updates. It's for addressing these more expensive updates or mitigating that issue that we would want to apply the new development with GPU architecture, adapting for the algebra and the solvers. The algorithm, though, that we use needs to be formulated in a certain way that meets the restrictions of GPU architecture. Of a special promise is the use of OSQP, so that interfaces well within GPU architecture. So our approach is based on proximal projection bundle methods. This is the general form. We assume a Slater type condition, which is easily met for our application. So these three steps just detail how what an iteration of PPBM looks like. It's like for this part, it's like ADMM. But we also have we maintain the residuals associated with primal dual feasibility with complementary slackness. We use this information to inform when we should add valid cuts, when we should reset the dual matrix, or when we should adjust row. Because our problem of interest, which is a continuous SDP, we're thinking branch and bound node subproblems. It satisfies Slater conditions, so we can carry the theory for ADMM to show that we have dual optimality in the limit, and we have limit points in the primal solutions that are optimal. The feature of adding the cuts, of course, gives it more, as mentioned, gives more affinity with the PPBM method. Now, as we add these cuts, the X update becomes more expensive. The Z update, not so much, because the projection involves taking eigen decompositions of small matrices. We'll see later on that the Z update takes minimal time. It's the X update that is the bottleneck. And that's what we want to address, the underlying linear algebra using the GPU architecture. So for computational experiments, we use Julia 1.4 with the jump modeling interface. We built on the power models package, and that package was helpful. It automates the chordal decomposition reformulation nicely. For our experiments, we use IP-opt with the MA57 linear solver. So we do not use CPU quite yet. So we're still in proof of concept, and then we have our computing resources. We consider 4 IEEE case instances. We fixed the budget at 4. We consider 3 starting rows. These are the other, and then the other parameters for the experiments, including the tolerance, maximum number of iterations, and so on. We compare ADMM for baseline comparison where there are no cuts, no adjustments of row. So we tabulate the results. We see that for the baseline ADMM versus PPBM in the objective column, for PPBM, we're closer to the a priori known optimal values given by ref. We also see that the residuals vanish more readily with PPBM due to the cuts, but due to the cuts, we also have the X updates taking longer time. So we have longer running time to terminate, even though the solutions are more accurate. We also have the plots which are in the paper. I'll only focus on the plot in the lower left-hand corner. For that, we have timing profile of the different steps of PPBM. And we see that the X update, again, takes the most time. Not only that, but we see a clear trend where once we add cuts, the amount of time for carrying out 100 iterations spikes noticeably. So we don't add many of these cuts for that reason, but if we could add more of these cuts, we would get, we expect to get noticeably faster convergence. And that is where we would interchange the X update with another GPU-based solver. Michel did preliminary experiments on GPU, so he replaced the use of IP-opt in the X update with OS2P interface on a GPU architecture. He was able to get successful results using case 9, case 30 after tightening the tolerances, but we couldn't get the same results for the larger problem. So that involves some fine tuning, debugging. That's an open question right now. So far, what we have is proof of concept. We have an algorithmic framework that interfaces nicely with the requirements of GPU. We're working out the details now of interfacing that with a solver for a large-scale convex quadratic program. So PPBM, it's designed to interface with GPU. It has some interesting features like the rules for adding cuts, the rules for changing row. These are non-trivial rules within any ADMM framework. There's always room for improvement with these. Our approach could stand to have additional insight with how PPBM relates with the other approaches, which we described to some degree. We also would want to, we focused on SBP, but we'd also like to look at other relaxations like the quadratic constraint relaxation or the tightenings of the SOC relaxation. In the experiments, as I mentioned, we used IP-opt. We couldn't apply GPU directly to it. It's not portable because IP-opt and other interior point rely on sparse algebra and definite linear systems. So we need an adapted version of a GPU solver. We know that the subproblem is convex, so that's good. We can work with that. as mentioned, we have preliminary experience, but we need to address some underlying problems getting it to work with the larger problems. Once we address these thrusts, we should mitigate the bottleneck issue. We should realize a first order method that can solve these SDP relaxations in a scalable manner, and these can be embedded in, say, branch and bound methods that have applications in the security of power flow systems. That's the end. These are the references. And thank you for your attention. Let us know if you have any questions.
Great. Thank you very much, Brian. Are there any questions for him? So I will go for it, Hassan.
This is Hassan Hijazi from Lano. I have one question for Brian. Thanks for the talk. The usual problem with the first order method is to reach the same level of tolerances in terms of constraint visibility and optimality. You need a lot more iterations. I was wondering what tolerances you're using, and you think if this can be a problematic issue if let's say I want 1E-6 visibility guarantees or optimality guarantees.
In the numerical experiments, we used 1E -3. So yes, the measures that we introduced, like incorporating the proximal bundle framework, had in mind that notion of allowing for the any given tolerance to be reached more quickly. So for any ADMM framework, knowing the best parameter, in this case rho, beforehand, the one that will give the fastest convergence, that's not trivial. Adjusting the rows is also not trivial. In a proximal bundle framework where we had cuts, so in this case we can project onto, say, the Z update, so we don't need to use bundle method. We can use instead the proximal point that like hybrids with ADMM. And so these cuts allow for more flexibility and stability in how rho is updated. So it's in improving the manner, like analyzing more carefully, which is future work, like how to update rho, how to use the cuts, how to place the cuts most adequately. That's what would help to mitigate the underlying problem of the first order methods converging slowly.
Thanks, Brian.
I don't see any other questions in the chat. I'll ask hopefully
Looks like
a quick
there's one more from Dan.
Oh yeah, there's one in the chat. So Dan says, could you estimate the crossover point in terms of problem size or computing resources where you would expect your approach to outperform interior point methods like MOSEC?
Okay, so I know that point hasn't been reached up to IEEE case 300. In that related paper that was referred to in the tables, even so, that paper had a different thrust. So we used MOSEC. So for getting the SDP lower bounds, within a branch and bound tree, we used MOSEC to solve the SDP subproblems. For that, we went up to some Pegas cases, 1354, 2869, and I mean there, yeah, we noticed that we could only apply MOSEC using chordal decomposition for those problems, but I haven't done numerical tests giving an idea of when even the chordal decomposition doesn't help with the MOSEC, when we really do need to improve the first order methods in order to scale to larger problems.
Great.
So,
I think that's a good answer, and still more to do.
Good question too.
Yep. Thank you very much, Brian.